Um, Welcome back. I'm going to talk more about learning in games today. But yesterday, in addition to lots of learning in games, we saw two ideas or techniques that are used a lot outside of game theory as well as in game theory, namely stochastic approximation for studying systems that slow down over time, and Blackwell's approachability theorem. Those are both used in many non-game theoretic settings. And today, I'm going to start off with another non-game theoretic concept that's quite useful, the idea of bandit problems. Because I'll be talking a lot about experimentation and information value, and I found that people don't always quite understand what I'm talking about, so I thought having a concrete illustration would be helpful.
Is it on?
Is it on? Probably not. Which is the on?
Yeah, that's a good question. Seems like it's on.
Ah, there we go. Perfect. It wasn't on. Now it's on. Good. So start with the case of one-armed bandit. It's a situation you have a choice between a safe arm with a known fixed payoff, say of M here, and a risky arm that has a fixed but unknown payoff distribution. If you haven't seen this before, I think the reason these are called one-armed bandits, this is originally a metaphor for slot machines, where you put in some money and you pull an arm, and if the things all line up, you get some money. Okay, so suppose you don't know the distribution on the risky arm. So here's an example. You know the possible payoffs. Either the risky arm pays you 2 or it pays you 0. You just don't know the probability of 2 and 0. So probably P of winning 2, probably 1 minus P of winning 0. Okay. Now, this particular example can be very simple. Your prior has 2-point support. With probably 0.4, you think P equals 1, which means that the arm always pays 2. With probably 0.6, you think P equals 0. The arm never pays 2. Well, then the expected value, if you pull the risky arm once, what's the expected value? There's a 0.4 chance of getting 2. So it's 0.8. That's the value of expected value of one pull of the risky arm. Suppose that the alternative is pulling the safe arm, and you get 0.9. So if you're purely myopic, or if you're playing this once, you should pull the safe arm, because 0.9 is more than 0.8. Now suppose you're playing it multiple times and you're not completely myopic. You care about the future. So you could just pull the safe arm, get 0.9, learn nothing, pull the safe arm, get 0.9. That's one feasible strategy. Something else you could do is try the risky arm once. And if it gives you a good payoff, well, now you've learned it's always going to pay 2, so you'll stick with it. And if it gives you a bad payoff, go back to the safe arm. So what does that pay? Well, probably 0.4, you've got the arm that always pays 2, and then you get 2 today and forever after, for average present value of 2. With probably 0.6, you get 0 today. That's not so great. But then tomorrow, you switch to the safe arm, which has 0.9. Okay? So it's 0.8 plus 0.54 delta. So which policy is better? Well, 0.8 is more than 0.54. 0.8 plus 0.54 delta is more than 0.9 if delta is more than 2/9, and if I did the algebra correctly. So I think 10/54, oh gosh, did I? 5, 2, yes, I think I did. Okay. So if you're sufficiently patient, you will pull the arm at least once. Then you pull it once. If you win, get a high payoff, yay, you stick there forever. 0 payoff, go back to the safe arm. Now this is a really easy bandit problem, because one pull was completely informative. Suppose instead your prior on P is uniform on 0, 1. So its expected value is a half, of course. And I'm going to increase the value of the risky arm now to be 4/3. So once again, the myopic player prefers the safe arm. 4/3 is more than a half times 2. Well, now one observation is not fully revealing, so it's harder to determine the fully optimal policy. But we can still say, can you do better than always pulling the safe arm? So you could still use this policy of try the risky arm once, and if it succeeds, stick with it forever, no matter what you see. Won't be optimal, but you could do that. So what's the value, well, if your prior is uniform and you binomial sampling, your posterior is beta with these parameters. And this is a special case of this Dirichlet distribution that I mentioned yesterday. So this is exactly the fictitious play type updating. The posterior expected value of P is A plus 1 over A plus B plus 2. So you can look that up, Math World or Wikipedia if you don't want to compute the integral and derive it yourself. So then, if you have exactly one success and no failures, you pull it once and succeed once, the expected value of P is now 2/3. It's a half a priori. If you pull it once and get a success, it increases. In this case, it increases to 2/3. So what's the value of this policy trying it once? And if it succeeds once, stick with it forever after, no matter what happens from then on. Well, with probably 0.5, you get the payoff of 2 today. So you have 2, 1 minus delta. And what's your payoff from now on? It's delta times the continuation. You're going to, we said in this policy, you stick with the risky arm forever after. You don't know for sure that the risky arm is good at this point, but you've probably 2/3 that the risky arm is good. So you're going to get 2/3 of 2 and 1/3 of 0. That's what happens if you have a success today. If you have a failure today, you get 0 today, and you switch to the safe arm forever afterwards. So again, if I've done the algebra correctly, the value of this policy is 1 plus delta. Which is better? Well, you can either have 1 plus delta, or you can just pull the safe arm forever and get 4/3. So if delta is more than 1/3, it's not optimal to stick with the safe arm. You should pull the risky arm at least once. Good? So this is what I mean by an experiment or option value. The risky arm has lower expected value than the safe arm if you could only pull it once. But there's a chance you'll learn that it's good. So it's worth trying it at least once for the information value. Okay? And this is going to be important in what comes later. As I said, this is not the optimal policy. How would we determine the optimal policy? We'd use dynamic programming. Okay? So the value given a posterior belief mu t and a value m of the outside option, what do? Either you stop today and get m, or you could pull the risky arm and get 1 minus delta times this reward today. RT is the reward of the risky arm today, plus the continuation value, so delta v, but now your posterior will be mu of t plus 1. And of course, we don't know what r is going to be. We don't know what the posterior will be. There's an expectation with respect to your current beliefs. So that's just the Bellman formula in this problem. Some facts about the solution of this problem. In general, for any fixed discount factor, what I'm calling experimentation, which is pulling the risky arm when its myopic payoff is lower than m, ends in finite time with probability 1. Okay? Meaning there's some finite time capital T so that at all later times, the arm you pick is myopically optimal. That makes sense, right? The reason you do something that's not myopically optimal is for the information value. Maybe you'll learn something. If you've pulled this arm a lot, you have a pretty big sample. You're not going to learn much from one more pull. At some point, the amount you're going to learn is so small, it's just not worth it. Okay? A consequence of this, there can be a positive probability that play quote-unquote locks on to the safe arm even though the risky arm would be better. So the true distribution of payoffs might be such you'd be better off always pulling the risky arm. You might get unlucky. You might get an unrepresentative sample 10 times in a row and you say, oh gosh, this doesn't look so good, and you stop. But if you knew more, you wouldn't. Okay, there's a positive probability of making a mistake in that sense. But the probability of this mistake goes to 0 as the discount factor goes to 1. And so you can show that, and you can see it heuristically. If you think of a time averaging case, if you were completely patient, then you can get the first best payoff by experimenting, doing something not myopically optimal, infinitely often, which gives you perfect information, but a vanishing fraction of a time So it's completely costless as far as time average payoff. Let me define the Gittins index of an arm and a belief, mu t, to be the largest value of the safe arm, m, so that you're just indifferent between stopping now and continuing with the problem. So the value of the problem is the value of the safe arm. I say largest. Now, that can't possibly be right. Must be smallest, right? Because if m goes to infinity, you're so smallest. Okay. The reason this is interesting, now let's consider not a one-armed bandit, but a k-armed bandit. There are k different arms you could pull. Independent. So you have independent beliefs on each arm. Each period you pick one arm. Then the Gittins-Jones theorem is that the solution to the multi-arm bandit problem is you compute the Gittins index for each arm as if it were the only arm. And each period, you use the arm that has the highest Gittins index. So this reduces this k-dimensional problem of which arm to pull to k different one-dimensional problems. So it makes things simpler, maybe not quite, it makes things conceptually simpler. So it turns out it's very hard to get closed forms for the Gittins index. If you actually want to use this, you typically have to do something numerical. Yeah. But this one?
No.
This one?
This one.
Yeah.
So suppose after time, I'm wondering whether you don't qualify the statement, but suppose after time t, you decide to use the risky arm, but you start getting bad rolls.
Yes.
So at some point, you would switch back to the
Safe arm. And once you switch to the safe arm, you stay there forever.
You would switch to this. Okay, I see what you're saying. I guess what confuses me is that suppose you stop getting bad rolls.
Yeah.
And you're just back to your initial prior. No, but in your initial prior, you use the risky arm. Okay, sorry.
Is it good?
Let's start. Yeah.
Good. Okay. Anyone else? This is important to say. Even if you don't do game theory ever again, this is still a useful thing to know about. Okay, but let's do some game theory. We're going to talk about extensive form games and self-confirming equilibrium. Because think of agents playing the game over and over, updating beliefs about opponent strategies, playing an extensive form game, and when you play the game, what you see is the terminal node of the extensive form. So you don't necessarily see the strategy of your opponent. You don't see how they would have played at unreached information sets. So then, incorrect beliefs about off-path play might persist. And play might converge to an outcome that is, quote, self-confirming, which I'll define, unless agents experiment in just the sense that I was talking about in the bandit problems. Okay, there's other possible information structures. I'm going to assume that people see the terminal node of the game. In some settings, it makes sense to assume that people observe less than a terminal node. Okay, for example, in a first price sealed bid auction, suppose all you see is the winning bid and not the losing bids. Well, that's less information than the full terminal. Right, the terminal node is it's the entire path of play, what everyone did. And if it's a game of incomplete information, if people had say, private values, the terminal node would be every player's value. Typically, you wouldn't observe that. So in some settings, it's interesting to say not only do you not observe strategies, but terminal nodes, you only observe partitions of terminal nodes. And that's been looked at in some papers I won't have time to discuss. Deckel, Fudenberg, Levine, Lehrer, Solon, Esponda, and Fudenberg, Kamada. You could also suppose that agents might observe the outcome, a terminal node, in other matches. They could talk to their friends and find out what happened in their friend's game. And that's an interesting concept that hasn't been looked at much in models of strategic learning. There is a literature on social learning, people talking to friends. It's usually about technologies or consumer goods, not about strategies. The questions we're going to have, what kind of outcomes can be steady states of learning processes? And there'll be different answers depending on the learning model we look at, self-confirming, rationalizable self-confirming, Nash, subgame perfect, etc. Some of this, quote, experimentation needs to be needed to rule out convergence to non-Nash outcomes? How much of this off-path experimentation is needed for various equilibrium concepts? How much off-path play has to occur in order that all steady states correspond to this equilibrium condition or that equilibrium condition? The answer will vary depending on the equilibrium condition. So here I'm asking how much experimentation is needed, and here I'm asking how much experimentation actually occurs. Okay? Again, that's a consequence of the learning model. Overview of the literature. First wave of papers on this, Fudenberg, Krebs, Cahill, Samet, Laslier, Walliser look at boundedly rational learning, meaning that they're going to make assumptions directly on the rate that agents experiment. Not going to derive experimentation, going to assume it. Okay? Paper of mine and Krebs looked at belief-based learning in the spirit of fictitious play with an extra assumption that agents experiment at rate 1 over t. What do I mean? So you compute your best response at each period, and you mostly do that, but you take a probability of order 1 over t and put it on every other action. Okay, that was just an assumption that we made. And we show that this condition rules out convergence to non-Nash outcomes, that if there's a steady state, it must be Nash when beliefs are asymptotically empirical, in the sense I defined yesterday, that they match your data. And the reason for this, to rule out convergence to a non-Nash outcome, we don't need that everybody has correct beliefs. We need that players on the path of play have correct beliefs, because they're the ones who, have to learn that they could gain by deviating. Okay, so, and what must they know about? These players on the path have to have correct beliefs about the relevant information sets, the ones that they could cause to be reached. If it's an information set that you can't deviate and cause to be reached, it's not matter for Nash equilibrium. Now this 1 over t experimentation rule, if people on the path play every action with the probability of order 1 over t, then every action that can be reached from the path, one step off the path, is reached infinitely often. Okay. Why is that? Because the sum of 1 over t is infinite. And we have what are called 0-1 laws, Borel-Cantelli, Glinko-Cantelli. If you have the sum of events, and each one, you have these probabilities that meet this bound that happens infinitely often with probability 1. But this exogenous 1 over t experimentation rule does not lead to correct beliefs throughout the path. Because to get to a node 2 steps off the path, 2 people have to experiment. So that's going to have probability of order 1 over t squared. 1 over t squared has a finite sum. Okay? So here we see a picture like this. Suppose that player 1 is mostly playing A, but experiments with B at rate 1 over t. Well, then 2 is reached infinitely often. 2, we hypothesize, mostly plays D, but experiments with C with probability 1 over t. And the probability of reaching player 3's node is 1 over t squared, finitely often, so wrong beliefs about 3's play could persist. So this much experimentation isn't going to be enough for, say, subgame perfect equilibrium, but it is enough for Nash equilibrium. Okay? So I said, if we assume people experiment in this way, this happens. That raises but doesn't answer the question, how much experimentation will people do? And note, if I had wanted to have a rule that got to player 3's information set there, I could have said people experiment at rate 1 over root t. And then it would have worked. So we need some guidance as to what kind of experimentation rates are reasonable. Now, another point, the solution to those bandit problems I showed you are deterministic, right? If you're solving a maximization problem, then except for borderline knife edge beliefs, you're not indifferent. You will either play the risky arm or the safe arm. It's not a general property of solutions to the bandit problem to randomize at any particular rate as function of time. Okay? So what to do about that? We can obviously say, well, this is descriptively descriptively realistic, 1 over t, we like it. Or, we could say, well, let's be really neoclassical. Everyone's maximizing discounted expected value. And that's what Levine and I did. We looked at this problem in a model with agents who are maximizing expected discounted value. And short version of what I'm about to show you, if the agents are myopic, the limits of our model are going to correspond to self-confirming equilibrium, meaning players learn the path of play but can have wrong beliefs about what could happen off. If players are arbitrarily patient, the limits, any limit state, I'll define these terms in a bit, must be a Nash equilibrium. So patient players will choose to experiment enough to rule out the non-Nash steady states.
But you can't get anything.
Well, we don't get subgame perfect. I think I'll have time. I'll show you a characterization of what we can get. We get something called subgame confirmed, so which is it's Nash.
You talked about that.
Yes, you've seen it before. Yeah, exactly. I mean, I talked about it informally Wednesday night. That's right. So that's the exact characterization of what this model produces. So notation, sort of players, game truth nodes X, information sets H, terminal nodes, pure strategies induce probability distributions over terminal nodes. This is all standard. Players know the extensive form of the game, except they may not know the distribution of nature's moves. You can either look at games of nature's move known or unknown. A probability mu I over pi minus I is player I's beliefs about the strategies of the other players. Okay, that's a measure over strategy profiles of the other players. For a mixed strategy profile sigma, let pi bar be the equivalent behavior strategy. And I'll say that player I's beliefs, it's sort of intuitively obvious what I mean if I say beliefs are corrected in the information set. Here I'm defining it formally. I's beliefs are correct at information set. So beliefs over this big set, all strategy profiles for all players. They're correct at an information set if I assign probability 1 to this lower dimensional subspace that coincides with what's actually happening at this one information set.
Players play few strategies.
I'm sorry?
Players play few strategies here.
No, not necessarily.
Why probability 1 might be randomizing?
The beliefs is a measure over strategies. Your beliefs are correct if they assign probability 1 to the strategies being correct at information set. So suppose that at information set 7, player 2 is mixing 2/3, 1/3. Okay, then I have, my beliefs are some long vector. Okay, and it's, what I want is that in the component that corresponds to what happens in information set 7, I put probability 1, it's on the subspace where 2's is mixing 2/3, 1/3. I mean, an easy, I don't have enough board space. But let me just so if this 2-player game and the other player only has 2 information sets, 2 actions each, then my beliefs about your strategies are in the unit square. And so then suppose what you're doing is 2/3. Okay, so my beliefs in general have support on the whole square, but if the beliefs that are correct at this particular information set have to put probability 1 on that vertical line. This is what I mean. So definition, sigma is a self-confirming equilibrium if for each player I and each pure strategy Si that has positive probability, there are beliefs mu I, which can depend on Si, such that Si is the best response to the beliefs, and the beliefs are correct at every information set that has positive probability when player I plays Si. So note this reduces to Nash equilibrium in one-shot simultaneous move games, because in this one-shot simultaneous move game, all H's are on the path of play. Okay? Note also that this allows player I to rationalize each strategy in the supportive sigma I with a different belief. And the reason for this is something I talked about Wednesday night. This is meant to capture steady states in a large population. There's many different player eyes, and different player eyes play different ways, see different things, and believe different things. Please. Louder, please.
When you say that the belief is correct,
Yeah, yes?
you mean that when I'm in this history age, if they would can see what the others did and
No, that's not what I mean. I mean, I have beliefs about your play at a bunch of information sets. So suppose I'm player, that's not a good example. Do I have one that's more? Okay, let's try this example. Okay, suppose I'm player 1, and I've always played across, and 2's always played across. Then belief should be correct at everything I have seen. So I have seen whenever 2 gets to move, 2 goes across. And so I believe that. I have never seen 3 play, so I put no restrictions on my beliefs about 3's play. So the condition is that my beliefs are consistent with what I've seen when I play the game. Yes, exactly. So it's called self-confirming. You could say it's not disconfirmed. It's not rejected by your data. That's the idea. Unitary SCE is a special case of SCE where for each player role, there's a single belief. All the player 1s believe the same thing. All the player 2s believe the same thing. So we can just define that. Okay. There's some related concepts I'll just mention in the literature to SCE. There's subjective equilibrium, conjectural equilibrium, and partially specified equilibrium. And all of these papers look only at the unitary case, and of them only Lever-Solon really looks into what happens with more than 2 players and the complications that arise then. Point out, SCE does not require that beliefs over strategies of the different players are consistent with a common prior. Why not? Well, this is something that Sergio mentioned yesterday. Aumann 87 shows that if we have a common prior over strategies, play is a correlated equilibrium. So we don't want to assume any sort of equilibrium here. We want to say, let's start with priors, let people learn and see what happens. So we don't want to assume equilibrium, we don't assume a common prior. For that reason, even in the unitary case, there can be self-confirming equilibria that aren't Nash equilibria, because 2 players can agree, or if you want, agree to disagree about the play of a 3rd player. And this is this example. I claim it's self-confirming for player 1 to play across and player 2 to play across. Player 1 plays across, believing that 3 plays right, because across gives player 1 1, and 1 believes that down gives him 0. Player 2 plays across, believing that player 3 plays left. Okay? So both players are best responding to beliefs. Their beliefs aren't disconfirmed. They're agreeing to disagree, but we're saying that's okay. This can result from a learning process in the style of fictitious play. Suppose players 1 and 2 start off with the kind of beliefs I talked about, and they play the game. When they play the game, 1 plays A, 2 plays A. 1 sees 2 plays A, increases the weight on A by 1, as in fictitious play. Didn't see 3 play, does not update beliefs on 3. It's as if 1 thinks 2's play and 3's play are independent. This outcome is not a Nash equilibrium. Oh, please?
Sorry, what is your disagreement about?
Oh, about player 3's play. I said that player 1 expects player 3 to play right. Player 2 expects player 3 to play left. So you could call that disagreement if you want. It's not a Nash equilibrium. Why is that? Well, suppose, let's look at a Nash equilibrium. There's something player 3 is doing. It doesn't matter what it is, but it's got to put weight at least 1/3 on one of left and right. It can't be less than 1/3 on left and less than 1/3 on right. And if it puts more than 1/3 on left, player 1 wants to go down. It puts more than 1/3 on right, player 2 wants to go down. So it's not a Nash outcome, but it's a self-confirming outcome. Okay, that's what I said. We can give a Bayesian interpretation in terms of independent beliefs, and it's not Nash. So that's one way that self-confirming equilibrium differs from Nash. 2 players can have different beliefs about the unobserved play of a 3rd player. Another way that it can differ from Nash is these heterogeneous beliefs. Different player ones can believe different things. So here's a trivial example just as proof of concept. I'm going to show you a game where there's no Nash equilibrium, where half the player ones go out, half go in, and all the player twos go A. Okay? So suppose our data is we have half the time we see this. So every time a 2 gets to move, 2 goes A. Half the time we see this. So this is not a Nash equilibrium, right? It's if 2 plays A, 1 should play in. It would be Nash for 1 to play out with probability 1, and then 2 could play B, so we'd see the outcome out. But it's not a Nash outcome to have half the ones going out and half going in. Because if one is mixing 50, if it's a single player 1 mixing 50-50, he forces 2 to play and he knows it. But this is the outcome of a self-confirming equilibrium. We could have some player 1s playing in and being happy when 2 plays A, some player 1s incorrectly fearing 2 plays B, they play out. They're wrong, but they get no data to prove they're wrong. They persist in their false belief. Okay, so that's a trivial example. Here's one that you may have seen before that's perhaps more interesting. This is a centipede game of McKelvey and Palfrey. Players take turns stopping or continuing. If they continue, the total value doubles. But it's better to stop today if you think the next player will stop tomorrow. And if the last player only cares about money payoff, she should stop. Backwards induction gives a unique outcome. Right? So backwards induction is 2 should stop. We have stop here, stop here, stop here, stop there. In the sort of, how to call this, these offset numbers here, that's the experimental probabilities of what actually happened at each information set. So it says only 8% of the player ones stopped at the first information set. Then conditional on reaching here, it was close to 50-50 on the 2s. Then conditional on reaching here, it was 3/4, 1/4. Okay? The backwards induction solution is player 1 should stop at the start. This data is not a Nash equilibrium. It's not a unitary self-confirming equilibrium, but it's a heterogeneous self-confirming equilibrium. The reason the heterogeneous beliefs are important is the money payoffs of the player 1s here are not the same. Who's making a big mistake here? The player 1s who play the backwards induction solution and stop at the start make less money than the player 1s who continue. So these guys are believing in backwards induction, stopping, getting their 0.4. And it's not that they like having less money, is our story. They would like to have money. They incorrectly think people are playing backwards induction. They haven't experimented and learned what's happening. They have a wrong belief, which is not rejected by their data. No, it is not a Nash equilibrium. This is not. If it's a Nash equilibrium, so this is not Nash. Every information set here is being hit. So then 2s here can't do this. All the 2s should do this. This is, trust me, this is not Nash. It's not even unitary self-confirming, which is weaker than Nash. It's not unitary self-confirming because different strategies of player 1 give different payoffs. And, with unitary you have the same beliefs, so you can only play different actions if you're indifferent.
I guess you can't reconcile with any equilibrium the choice of player 2 on the last stage.
Correct. Actually, that's not, let me think about this. So I said that, right. So I think you're right. So there have to be some group of player 2s who, have social preferences and prefer to go on. So to explain this, the last move we can't do with money preferences. There's an error on the slides. Everything else we can. But general, please? because then they're playing a repeated game, and then I wouldn't expect them to necessarily learn how to play the equilibrium of a staged game. I'd expect them to be learning, about the repeated game.
So they might be matched with someone else.
I'm confused now. What's the proposed match?
Proposal is, no, but
If matched with someone else each time, then there is a large population. That's the view which I would like. I thought Alhanan was saying let's do it with only 2 players in the world.
But let's look at the beliefs of a particular player who is matched repeatedly.
That's what I'm trying to do. I thought that's what Alhanan was asking me to change. That's exactly what I'm doing. Let me go on for a bit. Because I like questions, but let's move them back and forth. Okay, so what factors can lead self-confirming to differ from Nash? Well, I've shown you 2. The heterogeneous beliefs can obviously make a difference. There's one I haven't shown you, but hopefully you can construct an example on your own pretty easily. Correlated beliefs. Suppose player 1 can go in or out. In gives the move to players 2 and 3 who play simultaneously. Okay. Now player 1 is sure that 2 and 3 play some pure profile, but he does not know if they're playing up, left, or down, right. His subjective uncertainty is correlated. It might be that subjective belief keeps player 1 from playing in, even though he has to play in any Nash equilibrium. So that's this correlated beliefs problem. Inconsistent beliefs I have shown you. This is where players 1 and 2 disagree about the play of player 3. So here's 3 ways self-confirming and Nash can differ, and David and I showed this list is exhaustive. That's the only 3 ways that self-confirming and Nash can differ. I won't quite state that theorem. I'm going to state something that's maybe a little simpler and more salient. To do that, for any pure strategy profile, or any mixed strategy profile, even let h bar of S be the path of S. It's the information sets that are reached with positive probability. Okay? I'll say a game, okay, so these are pure strategies. A game has observed deviators if for all players and all pure strategy profiles S, and consider any alternative strategy S hat I for player I. If H is reached when player I plays S hat I, holding everyone else fixed, but it was not reached on S, so that means that H is reached if player I unilaterally deviates, then there is nothing that everyone else could do, no S hat minus I for everyone else, such that H would be reached if player I did not deviate and stayed stuck at Si. Okay, so if player I can deviate and make H be reached, if player I does not deviate, H can't be reached. Well, that means if we see H, we know player I deviated. Okay? So that's the consequence of this definition. What kind of games have this property? Well, games of perfect information trivially satisfy this condition, as do all multi-stage games with observed actions. So say the repeated prisoner's dilemma meets this condition. If someone deviates, you know who deviated. It's also always satisfied in 2-player games, at least if they have perfect recall. There's only 2 guys and someone deviated, and you remember you didn't deviate, well, there's not many people left. It could be. It holds in many economic applications, but not all possible games. This 3-player game I showed you with the inconsistent beliefs was originally due to Selton. He used it for something else. It's called the horse game because people think it looks like a horse. Whatever. Or you could say, there's after recess, the class comes in and someone has written something naughty on the blackboard. And the teacher doesn't know who did it. So that would be a game without observed deviators. So there are cases without them. Independent beliefs just means the beliefs are a product measure, but both on and off the path of play. And the theorem, which stated and mostly proved in the 93 paper, but there was an error that was corrected by Yuichiro Kamada in 2009, is that in games with observed deviators, like the prisoner's dilemma, the outcome of any independent beliefs, unitary, one belief per side, self-confirming equilibrium is the outcome of a Nash equilibrium. Okay, so the observed deviators condition basically shuts off the importance of inconsistent beliefs, and I've assumed the other two channels away, and we're down to Nash. So note, the proof does not say an equivalence of profiles, equivalence of outcomes. You give me a self-confirming strategy with an outcome, I'm going to build a different profile with the same outcome. That's a Nash equilibrium. And how do you do this? Well, unitary beliefs means I can talk about player I's belief. That's a well-defined thing. There's not 18 different things player I could believe. Independent beliefs is handy because so one's beliefs about players 2 and 3 looks like a strategy profile. Kuhn's theorem will let us map beliefs to strategies person by person, but with correlation, we can end up with a correlated profile. Independence means we do Kuhn's theorem and we can represent player I's beliefs about his opponents as a point mixed strategy profile. The importance of observed deviators, at any given off-path information set, notice one step off the path, only one guy's beliefs matter. Whose beliefs? The guy who can make that information set happen. No one else's beliefs matter because they can't make it happen. So it's an off-path information set. Nash equilibrium doesn't care about optimization off the path. Let's take the guy who's playing at that information set and tell him to play the way the on-path person thought he was playing. And now that guy has correct beliefs. We'll tell everyone else the truth also. It doesn't matter what their beliefs are. They can't make this information set happen. So we can build an information set, build a strategy which is Nash, has the same outcome. Okay? So that's equilibrium concept. Now, how about the learning model? There are various learning models that have self-confirming as a long-run outcome. I'm just going to present one of them from the companion paper with David Levine. This is the one on optimal Bayesian experimentation and so on. So our agents are going to have finite lives. They're going to live capital T periods. And they're going to maximize discounted per period sum of expected utility, completely standard. Each time they play the game, they'll observe a terminal node. Agent believes he faces a fixed time-invariant distribution of opponent strategies. Does not know what the distribution is, as in the bandit problem. Right? There's some probability P if the arm is good. It's the same idea. I'm not going to assume a functional form for the prior, but I'm going to assume the prior is non-doctrinaire, which means it has a continuous density that's strictly positive on the interior. Now, so this allows the density to go to 0 at the endpoints. Why do I bother with that and not just make it positive everywhere? Because I would like to nest fictitious play in Dirichlet priors, and those go to 0 on the boundary. So this actually matters, this generality. Players update their beliefs given Bayes' rule. Non-doctrinaire prior, you get a signal, you update, you'll have a non-doctrinaire posterior. Each agent faces a dynamic programming problem here, just like the Bellman equation of the bandit problem. I'm not going to solve it. I just want some notation for it here. So yi is a set of all the histories that player I could see. He starts off as a new player, he has a null history. He's played once, he's seen one terminal node. He's played twice, he's seen 2 terminal nodes. Any time he goes to play the game, he plays the game again, he has a certain past history, and he wants to decide what to do now. Okay? This is a discounted dynamic programming problem that has a solution. It might not be unique, just pick one, and we can make it a deterministic solution. Fine. That's what each player does. How about the aggregate? Okay. So this model is going to have lots of simplifying tricks with the end goal of being able to look at learning, which is a stochastic process where people's beliefs change, in a stationary deterministic system. Okay, so we're going to look at a continuum population. a unit mass of player 1s, a unit mass of player 2s, and so on. We're going to have not just an infinite horizon, but a doubly infinite sequence of periods. So we're going to start off at time minus infinity. And overlapping generations. 1 over t players in each generation. Okay? So at each time period, at the end of the round, the oldest players leave and new people come in. So I like to tell my class, this is my macro paper, right, of overlapping generations and doubly infinite time. What happens, each period, each agent is randomly matched with one agent of each other population. So player 1 meets a player 2 and a player 3, etc. When you meet people, you aren't told anything but, okay, you're playing the game, what's your choice? You don't know how old they are, how many times they've played. You don't know their past observations, what they've done. It's just each period you're anonymously matched with someone else. And to lighten notation, each population, all the player 1s have the same prior. And I could have different, a finite collection of priors, and different player 1s have different priors. That just adds extra subscripts, okay? The state of the system now is the fraction of the population with each history. So suppose t is 2, so half player 1s are young, half are old. The young ones have a null history. The old ones, maybe there's 4 different things they could have seen, so we'll have some weight of the old ones who saw player 2 do this, old ones who saw player 2 do that. That's the state. For a given distribution for a given distribution on the space of strategies, we can compute the fraction of the population that would have every possible history. So if some player 1s are playing heads, some are playing tails, we know what the player 2s will have seen on average. We can compute that. That map is continuous. So the point of all this is this system has steady states. So we succeeded in looking at learning, which is a stochastic problem where people are learning in a steady state system. What are the tricks? Well, to get rid of randomness, we have a continuum population and implicit appeal to the informal law of large numbers in defining the system dynamics. But even still, if everyone is learning, the system changes over time. So how do you have a steady state? If you have more and more information coming in, information has to leave. And the finite lifetimes are like a memory loss. Right? You could, instead of people dying, at time t, we could just mind wipe them. That'd be exactly the same. If you want a steady state in the learning system, information comes in, it has to go out. Okay? So that's the point of this system. What are the steady states? Well, if a lifetime is 1, no one can learn anything. You're born, you play a best response to your prior, you leave. That's a really boring steady state. It would be nice to say something about what happens with intermediate lifetimes. No one has done that, but I think this is a sort of a tractable seeming model where maybe something could be said. And the kind of thing you might be able to say, if you have a lifetime of 10 or 8, then there's a non-trivial chunk of new players each day. And then, for the experienced players, maybe they don't learn to play equilibrium, they learn to take advantage of the new players. And there are some settings where that sort of makes sense, like in some poker games. We didn't do that. We focused on what happens when the lifetime is really long. So the lifetime is really long. That means that most players are really old and have lots of data. So there's only a small share of new players in the system. And a bit of notation just to state things. Theta bar is a set of steady states. It depends on the prior, the discount factor, and the lifetime. Now hold the prior and discount factor fixed and let the lifetimes grow. And if it's a sequence of steady states, theta bar t converging to theta bar, we'll say theta bar is delta stable. Then if theta bar of delta is delta stable and we take people patienter and patienter, we get to theta bar, we'll say theta bar is patiently stable. So that's the outcome of the iterated limit where first the lifetime gets long and then people get patient. So 2 comments on this. It's suppressed in the notation, but the steady states depend on the prior. And that should be intuitive. If we're playing Battle of the Sexes and you start off with a non-doctrinaire prior with probably 0.999 that we're playing ballet, then everyone's going to play ballet, and as they learn, they'll see ballet, and we'll stick at ballet. We're not going to switch over to football, wherever the alternative was. So it makes sense that steady states depend on the prior. The order of limits here, the fact that we have a particular iterated limit, we don't know that's necessary. This is used in the theorem. It's a limitation of our proof technique that we haven't been able to prove this the other way. So the theorem is that these delta steady states, when people live long enough to get lots of data, must be self-confirming, and that patiently stable states must be Nash. So let me give intuition. First, for the self-confirming result, if a strategy SI is played a lot in the limit, then for large lifetime, it's played a lot, it's played a positive fraction of a time by a positive fraction of the population. But if that wasn't the case, it wouldn't have positive share overall. It has to be a non-negligible chunk of people who, they don't have to play it every day, they have to play it a non-zero fraction of a time. Okay? Now, of these agents who've played this strategy many times, we claim they mostly have beliefs that are approximately correct about what happens. Why? There's two parts to this. The law of large numbers says if you play the strategy a lot, your data looks like the theoretical distribution with high probability. Then, the paper of Diaconis and Friedman says that if you have a big sample, your posterior beliefs look like the data, and they converge to the data at a uniform rate. So you don't have to worry about, with some screwy samples, your posterior might be far from the data. It's a uniform rate that posteriors converge to the data, and this is the part of the proof that uses the non-doctrinaire prior assumption. They used it, so we use it to be able to use their result. Last part, as in bandit problems, agents eventually stop experimenting and play a myopic best response to their beliefs. I've told you they get correct beliefs, but they're self-confirming, they must be best responding to beliefs. So that's related to what happens to bandit problems, but there's an additional small complication of bandit in games that comes from the fact that players know the extensive form. And at this point, if you could put up the screen, please. Oh, but you can leave it. That's okay, whatever. So, in this game, player 1 plays left or right. Player 2 simultaneously picks A or B. Player 3 only gets to move if 1 goes R and 2 goes B. Okay, suppose that we've played the game many times, and the empirical distribution of play looks like this. 1/4 of the time left A, 1/4 of the time left B, and a half the time RA. Okay, that's data that player 1 might have.
There is an information set for player 2.
Yes, and there's an information set for player 2. Player 2 can't tell here versus here. That's correct. Okay? Now, player 1 is going to compute the probability that player 2 plays A is a half, and the probability that player 2 plays B is a quarter. So player 1 thinks that if he were to play right next time, there'd be a 1/4 chance of getting here. Maybe playing here is really good for player 1 if player 3 makes the correct decision. Say, okay? So if player 1 thinks there's a 1/4 chance that by playing right, we'll get the move down here, player 1 assigns an information value to playing right. Maybe I'll learn something. Even though he's already played right millions of times, he still thinks he has information value. So in this case, you'd worry maybe player 1 would not be asymptotically myopic. He would keep on experimenting forever. Well, as was pointed out, there's an information set here. So while this could be the data, it's really unlikely if 1 and 2 are mixing independently. So there are some screwy information sets where people might keep on experimenting and not being asymptotically myopic, but you can show their probability goes to 0. So that's what I meant by a small complication. Okay. Back up. The next part of the result is that if we now let people get patient, we end up at Nash equilibrium. Okay? Well, that was a very easy result to prove if we just assumed 1 over t experimentation. We used the 0-1 law, we got to the information sets we needed, problem solved. But as I said, for generic beliefs, players don't randomize. Okay? So actually, okay. I'm sorry. Last time, back up. I just could have read these words without them seeing it. I've one more figure which shows a more important complication. So this problem our players solve is a lot like a bandit problem, but it doesn't have independent arms. In fact, some of the arms are perfectly correlated. And that makes characterizing the optimal rule hard. With the 1 over t experimentation, you took every action with probably 1 over t. Some actions might never make sense as experiments. Okay? And that's the case in the figure here. Player 1 can play left, and they both get 2. Middle and right both go to an information set for player 2. And if player 2 is playing A, then middle is good, gives 4. Playing B, it's bad. If player 2 is playing R, then if player 1 plays R, he gets a sure 1, regardless. Suppose that player 1 thinks probably player 2 is playing B, but maybe player 2 is playing A. Maybe I want to experiment and just give 2 the move to see what's going on. How should I do it? Well, M and R give exactly the same information. These are correlated arms. The expected loss of playing R is just 1. You give up 1 instead of 2. If you think 2 is probably playing B, there's a really big loss from playing this. So you would never play this as an experiment. You would, if you thought the probability of B was high, you'd play R. Okay? So we're not going to be able to show every action is played infinitely often. And as an aside on how different the learning approach is from refinements that are based on axioms and so on, note that this action, call it left, dominates this action. So Kohlberg-Mertens stability would say we could prune this, and if 2 gets to move, 2 should think, oh, it must be middle, and 2 should play A. That's a story where if 2 gets the move, player 1 meant to give 2 the move forever, all the time. If we're in a setting where player 1's mostly play L, and they only give 2 the move occasionally as an experiment, the whole logic changes. Okay? For this reason, it looked very hard for us to solve the bandit problem in the way you solve the Gittins problem, and instead we resorted to an indirect proof. Instead of saying how much do people experiment and what's the optimal strategy, the indirect argument is going to say people keep on experimenting in certain situations. So how does it go? So if we've gotten to a steady state, people are playing this action a lot, they have a lot of data on it, they're mostly playing it because it's a good idea, not as an experiment. This is this bandit type result. For any discount factor, you stop experimenting. If our limit's not a Nash equilibrium, then there's some strategy being played that's not optimal. And we're going to show for contradiction that if you're playing something that's not optimal, you would have kept on experimenting. Here we say you have to stop experimenting. Here we say you don't stop experimenting. Why is that? If a steady state is not Nash, someone can gain at least k by deviating. Let E be all the strategy profiles where someone can gain K or more. The priors assign positive probability to the set of strategies in E. Why? Because we have this non-doctrinaire priors. They assign probability bounded away to 0 to every set of strategies. So you start off with some non-zero probability on the set. Might not be big, but it's not 0. Law of large numbers says you're unlikely to have a sample that hits an information set many times and is different than the theoretical law that corresponds to the strategies being played. So that means you're not going to get a very large and very misleading sample. Your prior gave this thing weight bounded away from 0. Your posterior gives this set E weight bounded away from 0. So you have this set E where if the opponent's strategy are in set, you do much better. And that means that if you're sufficiently patient, you have an option value from reaching the set. So you keep on experimenting, and that's the contradiction. Conclusion, patient players experiment enough to rule out non-Nash steady states. But as Eric was alluding to, this doesn't say that all Nash equilibrium are limits at steady states. It's not the converse. And we looked at that in a later paper, but only in games of perfect information with independent beliefs. Why did we do that? That really simplifies optimal experimentation and inference. Okay? Now, unlike in my picture there, there's no reason for a player to take action 1 to learn what would have happened if he played action 2, because they're going to go to different information sets. So now the bandit problem becomes much simpler with perfect information and independent beliefs. With correlated beliefs, maybe I play this action to see what happens over here. Independence. Okay, so this makes life simple. And we show that for some, not all, non-doctrinaire priors, the players in the limit, the players off the path of play choose not to experiment, no matter how patient they are. It might be a little counterintuitive. If you're really patient, why do you experiment? Well, if you're being reached really, really infrequently, there's no point. But the off-path play isn't completely arbitrary. Players on the path of play do experiment. So players one step off the path of play are reached infinitely often, so their beliefs at least have to be self-confirming. So node X is one step off the path of a profile. If it's not reached under the profile, it's probably 0 under pi, but it's an immediate successor of a node that is reached with positive probability. So if some player deviated, we would reach the node. Profile pi is subgame confirmed Nash equilibrium if it's Nash, and if each subgame one step off the path, the restriction of pi to the subgame is self-confirming. And the theorem is that in simple games, this game's perfect information, no player moves more than once on any path through the tree, with no own ties. That's a weak form of generic payoffs. There's no actions a player can take where two different actions yield him the same payoff. It could give other people the same payoff, but not him. Any subgame confirmed Nash equilibrium that's nearly pure, meaning no randomization on the path, only nature randomizes off the path, is equivalent to a patiently stable state. So we can support any of these subgame confirmed things with the right priors in these games. Now, if we have a really short game, only length 2, subgame confirmed reduces to backwards induction and subgame perfection. But that's not true in games already of length 3, like the 3-player centipede game. Here the unique subgame perfect equilibrium, pass, because 2 beats 1 for player 3, 1 beats 0 for player 2. No, sorry. 2 beats 1 for player 3, 3 passes. 2 says if I pass I get 2, 2 beats 1, so 2 passes. 1 says if I drop I get 1, if I pass I get 2. So backwards induction, we go to the end of a tree, but drop, drop, pass is subgame confirmed. 2 drops out, does not learn 3's play. So 1's on the path, is mostly dropping, sometimes experiments. 1 learns that 2 is dropping. Given 2 is dropping, 1 should drop. Okay? 2 drops, and 2 is off the path. 2 does not experiment. 2 thinks that 3 is dropping, which is why 2 drops. So 2 is making a mistake. 2 is off the path. Some of you may have heard of one-step perfection of Kalai and Neme. So that's a bit stronger than Subgame confirmed. It's Nash equilibrium and Nash one step off the path. And they said, well, the Subgame perfection is Nash everywhere. We can have k-step confirmed. Nash k-steps off the path. So they defined it, gave examples. They didn't give a learning foundation for it. No particular reason given for why this should occur. So perhaps it's not surprising that these things are different. How much patience should we expect? So I've shown you some limit theorems. In the lab, we're never going to get a discount factor of 0.99999. You can't keep people in the lab that long. Okay? In what field settings do very high discount factors seem plausible? I'm not sure. This is sort of a question for thought. To what extent can word of mouth, social learning, or historical records provide extra information about off-path play? So this comes back to the question that in order to know how correct beliefs should be off-path, we have to know how much information people have. If it comes from experimentation, well, how much patience do we think people have? And this is still open as far as I'm concerned. That's the question this literature raises. We have different answers depending on the patience of the players. So what's the patience? Wish I could tell you. Okay, 20 minutes left. In self-confirming equilibrium, the only constraint on beliefs is what players observe. Now, you might think you'd want extra constraints. Like I've never taken you to this restaurant, but I know you don't like chocolate, so I'm going to predict you're not going to order chocolate dessert in this restaurant. So you might want to add in some payoff. I mean, in some cases, players don't have much payoff information. Other cases, they do. You might want to be able to add payoff information into self-confirming equilibrium. There's experimental evidence that if we give players information about opponents' payoffs, it makes a difference. For example, in Krasnokar and Roth. And in that paper, the difference in the outcomes corresponds to the difference between self-confirming equilibrium and what's called rationalizable self-confirming equilibrium, which adds in the idea that we expect players to act in accordance with maximizing their payoffs. Okay, this is a unitary concept, a single belief for all players, not because we suddenly thought that was the most realistic, but because that was easier. We're trying to extend that. I don't want to take time to give you the formal definition of RSCE, but I thought I'd show you an example of how it works on this game. Up for player 1 and up for player 3 is a Nash equilibrium outcome. Therefore, it's automatically self-confirming, but it's not rationalizable self-confirming. Okay, again, I'm not going to give you the definition, but I'm going to give you the intuition. Think about people's beliefs are consistent with their data, and they know people's payoff functions. Okay? Well, if this is the outcome, then everyone sees that 3 is playing up. Okay? So 1 knows 3 is playing up, but moreover, 1 knows that 2 knows that 3 is playing up, because we've all been seeing 1 play up and 3 play up. Now, if 2 knows that 3 is playing up, then 2 ought to play A and not D, because 2 is more than 1. So if 1 knows that 2 knows 3 is playing up, and 1 knows 2's payoff function, 1 should say, if I play right, 2 plays A, I get 2, that's better than 1. So by combining knowledge of the path and knowledge of payoffs, we get in constraints stronger than Nash equilibrium. Okay. This was comparatively easy because everyone saw the same outcome. If players only see partitions of terminal nodes, like as suggested in sealed bid auctions, different players might have different partitions. Now there's not a commonly known outcome, And you'd like to do the same kind of arguments, but it's just more complicated. So that's work in progress. I'll skip the example in interest of not wearing you out. We can come back to this. Actually, I'm going to have time for some discussion. We'll come back to that or else have more chat. Mistakes in inference. Both self-confirming equilibrium and rationalizable version of SCE assume that players' inferences are consistent with their observations. There's a related literature that assumes people make systematic mistakes in processing information. One of them is Jahil's idea of an analogy-based expectations equilibrium, or ABEE. So the idea here is that players group their opponent's decision nodes into, quote, analogy classes. And players believe that play at each node in a given class is identical. Given this, beliefs have to correspond with the averages. It's like self-confirming in that you're matching your beliefs to some data, but you have the wrong model of the game. Please.
Sorry, I didn't understand. What is the difference between
Yeah, I'm sorry. I did that very quickly, and I didn't give the definition formally. The idea of the rationalizable self-confirming, it's a concept that adds in the idea that there's, more or less common knowledge of the payoffs. So player 1 knows player 2's payoff, and player 2 knows player 1's payoff. And if you're familiar with the concept of rationalizability, so this has a bit of that flavor. So each player has a version. If I'm playing something, it must be a response to some mental state I think you could have, where you're optimizing, giving something you could believe. So it's like rationalizability. One way of thinking about it, it's like rationalizability with the additional assumption that there's a commonly known outcome of the game that players converge to.
So because I was thinking this, because basically you need like a distribution over the other strategy.
Yes.
That's very circular, right?
Yes.
But then I'm thinking, so this belief also has to be consistent as in the
Yes.
okay.
Yes. Yes. Yes.
If you play that three-player game you had up a moment ago,
This
that
one? Yes.
If you play that in the lab,
No one has done that. That'd be interesting to see what happened. That's a fair question. It's in part. Yeah.
do we have experimental evidence of some form for self-confirming rational expectations? Rationalizable self-confirming.
So the evidence is of this Krasnikar-Roth form, and it mostly comes and the difference between this and standard solution concepts is mostly the heterogeneity. That there are many extensive form game experiments where different people doing different things, and none of the standard concepts make sense of that. The different actions different strategies only make sense with different beliefs. So there's multiple examples of that form. There aren't many examples of the non-Nash behavior where player 1 and 2 disagree about the play of player 3, because almost all the experiments have observed deviators, which makes that impossible. So this is a conceptual problem, but it's perhaps economically, people don't think it's important because they're not doing those experiments. But this one is simple, but easy to do in the lab. It's a little, I guess the thing is that the issue is we don't usually show people information sets and game trees in experiments. We look for designs that are easy for subjects to understand. And the concern is that this is such a unfamiliar looking object, people will just be baffled for a while. So it'll take lots of, I'd be delighted to know what happens. So let me give an example of this ABEE, very stark example. Nature moves first, choosing state A with probably 2/3 or B with probably 1/3. Player 1 moves second. It's a game of perfect information. So player 1 sees nature's move, and player 1 picks either A1 or B1. And player 2 moves last, getting A2 or choosing A2 or B2. And player 2 is a dummy player, getting payout 0 no matter what. But let me specify a strategy for 2. Suppose that 2 picks A2 when nature went A and B2 when nature went B, irrespective of what player 1 did. Okay, that's a strategy for player 2. Player 1 wants to match player 2. Player 1 gets 1 if he matches player 2 and 0 if not. Okay. Then what should happen, in state A, player 1 should play A1 because 2 is playing A1, and in state B, player 1 should play B1. That would be the best response for player 1 to player 2 strategy. Now, ABEE, there's not a unique ABEE because there's not a unique analogy class. We can pick any analogy class we want. Let's suppose that player 1 views all nodes of player 2 following a given move as belonging to a given analogy class. This loops them all together as if player 2 is observing nothing. Then what player 1 sees, player A plays A2 2/3 of the time. So player 1 says, I'm going to play A all the time. Okay? Now, if player 1 does this and keeps track of the terminal nodes of the game, it's true, he will learn that player 2 plays A 2/3 of the time, but he'll also learn that 2's play is correlated with nature's play. So if he was a Bayesian, and if he assigned positive probability to player 2's strategy depending on the state, he should learn that player 2's strategy depends on the state. So how to make sense of this ABEE, where player 1 is consistently ignoring the evidence? Well, one way of thinking about it, it's an approximation for a Bayesian. Suppose the player 1 thinks, yeah, I have a non-doctrinaire prior, but it's massively, like 0.999 probability on player 2 ignores the state, and only very small chance. So then you could try and rationalize this as saying that it would take player 1 a long time to learn if he had a strong prior. I don't know. Or you could say that the player 1 simply can't remember all the past data. Maybe all player 1 can remember is what player 2 is doing. He sees nature's move, but he has a very constrained memory, and he's just able to remember what player 2 did. Okay? So that's a story. I don't know. So this ABEE corresponds to self-confirming equilibrium, where what player 1 sees is not the terminal node, but only player 2's action. Player 1 does not get to see his own payoff, does not get to see nature's move. If all the feedback you got was player 2's action, well, then it makes sense to do the thing that 2 does most of the time. But that's not the assumption here. The assumption is that player 1 did see it all, but ignores it. So that's built into, this is a particular kind of error in analogy-based expectation equilibrium. It's related to something from behavioral economics, the cursed equilibrium of Aister and Rabin. So they defined a whole family of cursedness levels. The simple one to think about is the fully cursed equilibrium. So this is play in a static incomplete information game. And you're fully cursed if you think your opponent's action is independent of their type. So if you think, say, of Akerlof-Lemon's problem, they're the low-value car owners, the ones who sell the cars, the high-value people keep the cars. The cursed person thinks the probability that sellers sell is a constant independent of a seller's value. That's what it means to be fully cursed. And then partially cursed is your beliefs are a convex combination of fully cursed and correct. And it turns out that this cursed equilibrium is a special case of analogy-based expectations equilibrium for a particular analogy class. This is shown by Miatnin, 2007. Okay, so there are ways to use these to incorporate some mistakes and behavioral problems with the idea of self-confirming equilibrium, and that beliefs have to somehow be constrained by the data. So instead of going back to the more technical material I jumped over, I thought it would be more fun to spend our last 10 minutes with an informal discussion of some open questions that I'd like you to think about. This is sort of a grab bag of questions. Some are well-defined and hard, and some are hopelessly vague and may or may not be hard, but they're food for thought. Okay, open issues in literature. things I would like to know the answer to. So yesterday, Sergio was talking about the set of outcome distributions that can be induced by the sorts of calibrated or regret-based rules he was discussing. And at one point he said, well, they were general correlated for a general meaning of the word general. He expressed some optimism that this general set was fairly large. I suspect it's perhaps not so large, but either way, it'd be nice to know. So this is an open issue. Something else that was alluded to yesterday, I talked about recency, and I said, well, it's the results we have now about recency in learning in games are all in the limit as the recency vanishes. And the cases we are more interested in is maybe when the recency doesn't vanish, and we don't quite know what to say there, what a good result would be, and wouldn't hope for a completely general statement of what intermediate recency does in all settings, but just some kind of worked out examples of the different effects of recency and what its implications are would be nice. I just very quickly showed you this result about subgame confirmed equilibrium. So that's the result of patient rational learning in simple games. Simple games is a very restrictive class of games. It would be interesting to have an extension of this result to some larger class of games. Things to point out there, to do this extension, before you prove whatever the theorem is, you need to have a equilibrium concept that will be good in this larger class of games. One of the nice things about simple games, they're perfect information. So every information that's a singleton, we didn't have to worry about assessments in the sense of Krebs-Wilson and sequential equilibrium. If you tried to do something like this in a game with non-trivial information sets, then you'll have to do something about these off-path beliefs of players who have multiple nodes in an information set. So we need that definition along with the extension of the learning theory. Yeah, hold on.
Your theorem?
Yes?
I mean, isn't your theorem, what is it? Your theorem does that, no?
Our theorem is only for the class of simple games.
No, the theorem before that.
Oh, so that's for all games. So there's two, okay, yes. So the earlier theorem holds for all games, and it says that if something is patiently stable, it must be Nash. But what's open is the converse. So if patiently stable, it must be Nash. That did not say that all Nash were patiently stable. In fact, not all Nash. We can show that some Nash are not. And so it's, in a simple case, it's subgame confirmed. So so what's the analogous smaller set than Nash? If people are patient, not only do the people on the path learn enough to rule out deviations, there's something gets learned off the path. And how much? That's what we don't know. So that's a well-defined problem. I don't have a clue. This one is less well-defined. There's the idea, that people extrapolate between similar games. And at some level that must be true. If you take a very narrow idea of what a game is, then each instant is a different game, and you never play the same game twice. But then that's the basic problem of inference. Every instant's a different instant. If you don't think tomorrow has something to do with the past, it's impossible to learn. So any kind of learning involves extrapolation. Old data helps you predict the future. It would be nice to have a bit more structure on how people extrapolate between games. I've seen a couple very simple attempts to do this, nothing I view as that great. It'd be nice to have some better results. So ABEE has been used a decent amount by Jahil and co-authors and students. It's always, let's take this setting, let's look at this analogy class and see what happens. It's unknown what the implications of ABEE are without restrictions on the analogy classes. If we just take this as the concept for any analogy class, what can happen? Open question. I talked a little bit last time about stochastic choice, the idea that in some settings there's evidence that people play stochastically. And also I said that stochastic choice in some ways helps us, at least in a static setting, with the learning models. It helps with the calibration results. It helps with smooth fictitious play. If we believe in stochastic choice in extensive form games, then in a sense, in the very long run, this whole problem with not seeing things off the path goes away. Because if there's a uniform lower bound on probabilities of actions, we're eventually going to get all throughout the game tree. Okay? However, if those stochastic terms are small, it still might take a long time to get all these observations all throughout the game tree. So to say something interesting about stochastic choice and learning in extensive games, we need some idea of what the intermediate run is and how to say what happens over 10, 100, some useful intermediate period, because don't know how to do that. In particular, we don't have a useful working definition of intermediate run. That would be having a definition that works in some small domain would be nice. So I talked about cursed equilibrium and analogy-based. I said it'd be nice to know what happens with unrestricted analogies, with unrestricted mistakes. It would also be nice to know what kind of false analogies are relevant for which applications. So what kind of mistakes do people make when in their learning? Related to this is the idea of misspecification. You can think of how could this player one play repeatedly and never notice that two's play was correlated with nature's play? Well, if you're a Bayesian and you assign 0 probability to two conditioning on nature's play, you can't learn it. That's an extreme version of a misspecified model. What sorts of misspecification do we think would persist for a long time? And when would people say, gee, my model is just not fitting so well, I should throw it away and try something else? Okay, that's a sort of a hard question to formalize, but it's interesting. A more approachable question that I've been working on with a student, Gleb Romanuk, is to look at active learning, or experimentation, in particular models of misspecified learning. So there's a very elaborate theory of bandit problems of active learning with correctly specified Bayesians. There's a literature in statistics on passive learning with misspecified models. There's not yet really a literature on active learning with misspecified models. And if we want to have a learning foundation for some of these behavioral concepts where people make persistent mistakes, then it would be nice to have learning foundations to back that up.
So a misspecified model is just a model which has probabilities 0.
Yes, exactly.
Something that shouldn't have.
Exactly. This is what I mean. That's right. As in probably 0 of 2 conditions on nature. And I guess the argument is that in some settings, the space of possible models is so big it's almost unavoidable. You put probably 0 on some things, and maybe those turn out to be the right things, and then what happens? So it'd be nice to know what happens with this. First of all, in decision problems, and then once we understand that a bit, perhaps in games. And I've got 1 minute left for questions. Please.
Going back like several slides, or wait a bit. There is there was a few, but probably even back to the blackboard. Oh, wait a second, don't. So what if player 2 understands that the only way how he can get turned is when player 1 learning,
Okay.
and therefore he understands that player 1 is learning, and his player 1. So the further actions of player 1 are influenced by current actions of player 2, and therefore he takes some tries to make use of it somehow.
Okay, so there's a couple of different issues buried in that question. So one is this idea of 2 doing something now to influence future play of player 1. And I've shut off that channel with the assumption of a continuum of agents and anonymous random matching. So yes, the player 1s are learning, but I'm not going to play this particular player 1 ever again. So that channel is gone. But the question also raises a different issue, which I sort of didn't make explicit and perhaps should. Suppose that 2 does know the 1s are learning. Or suppose that 2 knows 1's path information, something I mentioned without formalizing. How do you put that in the model? Well, if you're a Bayesian, everything you know about the structure of the world before you have any observations is in your prior. So where would the idea that I know your payoffs come in, it would come in, I would put very low probability. If I'm pretty sure you don't like chocolate, that just means my prior puts very low weight on not like chocolate. If I believe that I am reached when people learn, and I know which action it is when they learn, that means that my beliefs, instead of being unrestricted by the data, we could add this restriction on the beliefs that I should put much more weight on the strategies that make sense when the player ones are learning. So the way to incorporate any extra knowledge a player has is to put it in the prior. And once you've done that, then all the apparatus proceeds as before. And I think I'm out of time, so we should go have last round of coffee and cookies before Eric talks.